asks you to say, because this is just a point, 0, 3, 1, 2, 9, it could have literally no meaning other than to be a point, 0, 3, 1, 2, 9. But in terms of this project, both of those coordinates have meaning. So when you talk about what the meaning is of any point from a situation like this, you have to be specific. And if you turn your project over, it says, make sure you use all relevant numbers and all relevant units. If you've had 096 here, you've had lots of practice with this. So we know that the unit on that is dollars. This is supposed to represent dollars, and this is supposed to represent the year 2000. There's lots of different ways of saying this. I'm just going to tell you one way you could have represent this point. You could say, in the year 2000, we estimate that tuition and fees at, public four-year institutions, blah, 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 is $3,129. So notice in my sentence, I see the meaning of the 0, which is the year 2000. I see the meaning of 3129 with its units. The meaning is right here in the phrase before it. So the next page where you had the point, let's see, what was one of the points? Was it 15 and 8904? That was one of the points for like number 6 or something. So here you'd want to say, our model, another way to say this is our model is predicting, because we're predicting in the year 2015, we're predicting that tuition and fees will be $8,904. So that's the prediction, okay? So the key here is this word. Some people said in 2000, the tuition and fees was $3,219. No, it wasn't. What was the cost of tuition and the average cost in 2000? What was the average cost of tuition and fees? $3,362. That was the actual cost, right? This is a prediction or an estimate. This is really an estimate based on, I'll take that, Dylan. Anybody else just come in? Hannah, can I have yours, please? An estimate based on the model, okay? So you've got to make sure you use both numbers or a word that might, sometimes when you have 0, you might use the word no. Like on the next question, when you had negative 8.13 comma 0, you said, oh, 8 years or so before the year 2000. Some of you said 1992, some said 1991. Some like figured out the exact day. Ryan figured out the exact day for 7.85. He told me it was November 6th, right? So I'm not going to look that up. I'm going to take his word for it. And how would you talk? You could say $0 of tuition and fees. Now, is that realistic? That just 8 years ago, it didn't cost anything to attend a 4-year school? No. So some of you actually said, this doesn't make sense. It's not realistic. This is what we call model breakdown. So our model didn't even last, wasn't even a good estimate just 8 years prior to where the data started, which was 2000. So try to give as much detail as you want and really be careful that you're not saying that the number that your model finds is the actual value. Unless it is. It might go right through one of the points, okay? But most of the time it doesn't go directly through one of the data points. Any questions on that? Okay, so let's start with class 9, polynomial equations, and start us off, Sam. Okay, someone else who's on class 9? Okay, Jesse? Okay, why do we call that? Thank you, Jesse. Why do we call that a 4th degree equation? 4 is the highest exponent, right? As you look all the way across the equation, the highest power or exponent you see is 4. Okay? Now, we haven't learned how to solve these types of equations. All we've done in this class is we've learned how to solve linear and quadratic. That's it. And even our rational equations, when we solve them, they either came out to be linear or quadratic. So now we're faced with this thing where we have x to the 4th, and then all this other stuff hanging around it, x to the 3rd, we got an x squared, right? So one of the things we're going to talk about today is that the classification, this comes under polynomial equations, but guess what? So doesn't linear and quadratics. Linear equations and quadratic equations come under the big umbrella of being a polynomial. It's just that we give them special names. We call them linear and quadratic. When you start getting with higher powers like 4, 5, 6, 7, we don't usually give them special names. We just call them a 4th degree or a 5th degree equation. So the main idea here is if we can use a strategy that we've used earlier to solve either a linear or a quadratic equation, then it'd be great if we could use that same strategy to help us today. And this strategy, the zero product principle, is so useful. And we use that. Let's review how we used it with a quadratic. With a quadratic, if we could factor something and create 2 factors equal to 0, in general, we call those A times B. If we can create 2 factors or more than 2 factors, we could have 3 factors or 4 factors set equal to 0. The key here is that it's all multiplication on one side and 0 on the other. Once you have a situation like that, you know something about the individual factors. To solve that equation, you say, when is my factor A equal to 0? When is my factor B equal to 0? And if by chance I happen to have 3 factors, then you have the possibility of a 3rd solution. Okay? So the zero product principle is not just 2 factors. We've only seen it with 2 factors because up to this point we've only solved quadratics. So the idea here with a polynomial equation is to get all your terms on one side, everything, and set it equal to 0, because this idea, this zero product principle, is key to solving so many of our equations. So the first thing we're going to do here is we're going to subtract 6x squared from both sides of our equation. Okay, so my new equation looks like this. Okay, that's the first step with any polynomial equation of these higher degrees. Now, and I didn't realize this until my next class, I have this never divide both sides by x squared. And I asked if my students knew why, and nobody did. And I said, that's all right, we'll come back to this question. But a tendency here is for people, when they see something like this, to say, oh, I'm going to divide everything on both sides by x squared, because then if I did that, I'd have x squared here plus 1x here equals 6. And then that feels more familiar to you. But when you do that, you could run into problems, and we're going to see why in a minute. Okay, so you never want to divide both sides. And the reason I have x squared here is because that's what the smallest power is here. You never want to divide both sides by a variable expression. So it could be x cubed, it could be x, it could be x plus 3. You just don't want to divide by, try to get rid of one of your terms here by dividing both sides by any power of x. So it's not just x squared. So some people took that literally in the first question. So you never divide both sides by any power of x squared. Of any power of x, sorry. Okay, any power. Does anybody want to take a guess why right now? Like, can you think of why we wouldn't want to do that? Yeah, Anna?
Well, I have a guess at your answer to the question.
Okay, let's take a guess and then I'll hear the question. Six. So the 6 is definitely attached to the x squared. But we're trying to figure out why I'm saying you can't divide both sides by x squared. Caitlin, you want to give it a try?
Does that have to do with the solution?
Yes, it does have something to do with the possible solutions for x and what it couldn't be equal to. What if I said one of my solutions for x was 0? What's x squared going to be? 0, I heard. How about a little more confident? If x is 0, what's x squared? 0. So if I divided both sides by x squared, what am I going to be dividing by? 0. Is that allowed? Okay. So we don't know right now what the variable is, and dividing by x squared, you could potentially lose one of your solutions to the equation. That's kind of an easy way to say it. All right. Now, what's your question, Anna?
When you're doing like factoring,
Yeah.
why are you allowed to pull out the x squared to make it a nicer number?
Okay. All right. We're going to get to that. Okay. Promise. All right. So we have to now take these three terms, because that's what this is. It's three terms. This is called a trinomial. Here they are. And we have to turn that addition and subtraction expression on the left side into a multiplication problem. We've got to factor it. And we have no factoring technique that's going to make it look like, say, two binomials, which is all a lot of us think about. Like when I say factor something, this is all people think about. Something like this that looks like this, say. This is what you think factoring is. Factoring is turning any addition and subtraction expression into a multiplication. This is one type of factoring, but the most important, or the first type you should always look out for, because it can be a saving grace. Always look for the greatest common factor as your first strategy for factoring. And that's what the x squared is here, Anna. When you look at this and you're asked to factor this, the only way you can factor this is to write it as x squared times x squared plus x cubed minus 6. So all I've done here, Anna, is I've said that this multiplication problem on the left-hand side. Oh, thank you. Yes. That this multiplication problem and this addition and subtraction problem are identical. It's just looking at it as a multiplication problem. So I can use this idea of multiplying things equal to 0. That's the key. Then you ask yourself, is this completely factored? Can I factor this anymore? Can I factor this second factor right here? Well, you say it's a second degree trinomial. That a lot of times that will factor into two binomials. If I can factor it, I may not be able to. Can I factor this? What's it look like? X minus 2, x plus 3, right. So now I have everything completely factored on my left side. I can say, what will make each one of those factors 0? So notice this is x squared equals 0. This is actually a baby quadratic equation, but instead of two answers, it only has one, because it's equal to 0. And there's only one number that when you square, you get 0, because 0 is its own opposite. If this was like x squared equaled 4, we know we got two answers, plus and minus 2. But 0 is its own opposite, so there we go. One of our solutions is 0. So if we had divided both sides of this original equation by x squared, we never would have gotten this factor out here. So we would have lost one of our solutions. It would have disappeared. That's problematic. And we would have been dividing by 0 in this case. Then you set this factor equal to 0, and you get x is 2. This is just a baby linear equation to solve. And then you set this equation equal to 0, which is another baby linear equation. And there are your three solutions. You should always go back and check. I'm feeling pretty confident that this is okay, so I'm not going to check it. And then how would you write it in my math lab? How would you actually write it inside the set notation? What order? -3, your smallest number first, comma, 0, comma, 2. Right. So for your homework, that's how you would enter it. For me, on a quiz or a test, you can just circle each of these. That's fine. Put boxes, whatever you want to do. Right? Any questions on this? So it's important when you look at a problem. That's why I'm giving you this study aid here. because you have to be able to recognize what category of equation you're in so you can remember the strategy. So when you look at something like this, this is different than anything we've done before, and it's different from the next couple of problems we're going to look at. So you need to start being able to look at a problem. The first thing you should do is say, what kind of equation is this? Which of these categories in this pink sheet does it fall into? Because once you can identify what type of equation it is, then you'll remember some of the strategies for solving it. Hopefully, you'll have your little study aid with you as well. Any questions on this before we go on? All right. Yeah, Jesse? Yeah? Yeah, because let's suppose I put the plus with the 2 and the minus with the 3. I would get a minus 1x in the middle, not a plus 1x when I did FOIL. You see that? Oh, yeah. Okay. So the good news is, Jesse, if you're factoring and you do your FOIL to check and the number's right, the coefficient of your middle term is like you've got the number part right, but not the sign. All that means is just switch the two numbers. All right. Okay. Anything else before we go on? All right, let's take a look at the next type of equation we're going to have. Okay, and you're going to have lots of chance to practice working with these today. I want to go over the equations, then I'll come back to the graphing calculator solutions. So the second type of equation you're going to have is a radical equation. It's almost like it's almost impossible not to be able to identify a radical equation because the radical hits you smack right in the face, right? You see the radical symbol there. It could be a square root, it could be a cube root, it could be any root. In this particular case, we're looking at a radical on the left-hand side. And so usually we say we want to isolate our variable term. And the problem here is we got an x and we got a square root of x. So that's the first question you have to face, the first dilemma. So we need to find what x is equal to solve this equation. So when you have a radical equation, your strategy is isolate that radical, right? Just isolate it. Get it all by itself on one side of the equation. So to do that, what would I do to this left side to get the square root of x all alone? I would subtract x. So I isolate my radical term, which is called square root of x, and I subtract x from both sides. Okay, so I'm going to do that first. I'm going to get the square root of x equals 12 minus x. And again, as a note of caution, when you have more than one term, whether you're working with rational equations or whatever, always put those parentheses. So any operation you have to do to that, you'll remember to include both the 12 and the x. Okay. So now we have to, solving equations is a series forming a series of inverse operations. When we have something simple like x plus 3 is 10, we subtract 3 from both sides because that undoes adding 3 to x. We undo it by subtracting 3. So we have to undo what's happened to x here. And x has had its square root taken. So how do I undo? What's the inverse operation of taking a square root? Squaring, right. So I have to square both sides. So I undo the square root by performing its inverse operation, which is squaring both sides of this equation. So I'm going to take my original equation and I'm going to square both sides. Here we go. We're going to square both sides. Okay. I had a long discussion with my first class because I happened to ask, what square root is this? And you see this symbol. And I was aware that a lot of people didn't really realize that this symbol represents the positive square root. If you want the negative square root of a number, you have to have the negative out front. So the reason I'm pointing that out is by introducing the squaring idea to both sides of the equation, you come back to x. And x right now has no plus or minus. But when it's under this radical, we're asking for the positive result. And you'll see what I'm doing in a minute. Probably is more than you really need to hear right now. So we square both sides. The square and square root undo each other. And now the only trouble students run into is squaring a binomial. Some of us still are kind of stuck with squaring a binomial. Okay, you square the 12, you square the x, and then your middle term, when you multiply this out the long way, 12 minus x with FOIL, your middle term is negative 12x and negative 12x. You just double that product right there. So if you're trying to do this quickly, you just remember that it's almost like you want it to be. You get the 144 and you get the x squared, but you've got that middle term. Okay. So what kind of equation is this now? Quadratic, right? And we just spent a whole class on Friday solving quadratics. So the first thing we have to do is set it equal to 0. So we get minus 25x when I subtract x from both sides. That gives me a minus. Where did it come from? 12 times negative x is negative 12x, and negative x times 12 is negative 12x. You just always double that product right there, Caitlin. Whenever you're squaring a binomial, you multiply those two things and you double it, because the inner and outer term are exactly identical. That's just sort of like the quick way to do it. So when you see, so the formula that you'll see in a book, in a textbook, for squaring a binomial, if you have a plus b and a minus b, they don't write it out and do FOIL. They just say the answer always looks like this: a square, multiply a times b and double it, and then b square. That's what it always looks like. This one's going to be a square minus 2 times ab plus b squared. So if you have something like this, x minus 4 squared, you got the x squared guarantee, you got your 16 guarantee. Then when you multiply these two, you get minus 4x, just double it, and you're all done. You don't even have to FOIL. But if you don't, if that, that's too much for you, just FOIL it out. It's okay. Use your distributive property twice. That's all FOIL is. All right, any questions on this right now? Getting down to this part. I'm just going to put the right-hand side in descending order, which says I'm going to put my highest power first, my next power, and then finally the 144. So if you were given this at your seats right now, how would you proceed? Which method for solving a quadratic would you use? What would you do? You would use the quadratic formula? Okay, let's take a look at that. So we have 0 equals x squared minus 25x plus 144. So A equals, help me, 1, B equals, and C equals 144. Okay, so here's an equation. The thing I write underneath it better be an equation. The equation is x equals. I'm actually solving this for x. X equals the opposite of b plus or minus b squared, which is 625, minus 4 times a times c, all over 2a. So x equals 25 plus or minus the square root of 625. And 4 times that is what? I get a 6 over here, I get a 7 over there, and I get a 5 there, I think, if I did that correctly. You can check me on your calculator. 25 plus or minus, and what do I get when I subtract that? I get a 9, I get a 4. Square root of 49 over 2. So that equals 25 plus or minus 7 over 2, which equals, so x equals 25 plus 7 over 2, and x equals 25 minus 7 over 2. So that gives me a 16. And it also gives me a 9. Okay. So this actually came out, your answers are rational. In fact, they're integers. Anytime you solve a quadratic equation and you get rational solutions, that tells you something. This tells me that you could have factored your original equation, the expression on your left side, or your right side, whatever side it's on. That tells me I could have factored it. What would the factors have looked like if x is 16 and x is 9? Do you know how to work backwards? If x is 16, to go backwards to your factors, they would have been set equal to 0. So if I take a step backwards, what would my factor have looked like up here? X minus 16, because I would subtract 16 from both sides to get 0. And if I go backwards here, I'd have to subtract 9 from both sides. So what does my factor look like here? If I subtract 9 from both sides? X minus 9. Right? We always go this way. We go from here to here, folks. If you have your answer, you just take it a step backwards. You just reverse it. So this is how I could have originally factored the expression x squared minus 25x plus 144. This is how it factors. 16 times 9 is 144. 16 plus 9 is 25. And the two minus signs make it negative. So originally, another approach would have been to solve this quadratic equation. Rather than using your formula, you could have factored this. You could have called this x minus 16 times x minus 9, and then you could have gotten your two solutions from there. However, do not stop. If you never have been in the habit of checking your solutions, anytime you see a radical equation, it's absolutely mandatory that you check. Because often when we end up squaring or raising a power to both sides of an equation to the fourth power or sixth power, we can introduce solutions that are what we call extraneous. They don't work in our original equation. So let's check this out. Our original equation was x plus the square root of x equals 12. Well, let me check out my 9 and see if it works. 9 plus the square root of 9 equals 12. Remember, this is asking for the positive square root of 9 only. So this is 9 plus 3 is 12. 12 equals 12. You're happy. That one works. Okay. 16 plus the square root of 16, does that equal 12? No way. 16 plus the positive square root of 16 is 4. 20 does not equal 12. So this equation has one and only one solution, and that's 9. That's the only answer it has. So you should, whatever you do for notes for studying, when you're doing radical equations, you have to check your answers. It's absolutely mandatory, or else you'll end up with a solution that's really a false solution. Okay. Any questions on radical equations? Nothing? Nothing at all. All right, we got one more. One more type. And what's that one more type called? Rational exponents. Ah, no. Thought we got rid of these things. Yuck. All right. So if you want, you can turn x to the 3/4 into a radical. And you can create a radical equation, which we just solved a minute ago. So I want to show you a method that's different than what we did a minute ago. All right. So the question here is, where do you start when you see something like this? Well, the thing that's really bothering you or gets you kind of all uptight is this little exponent right here. So just for now, we'll be in pretend land. And we'll pretend that this just says 3x minus 6 is 0. If I gave you that equation, what would be your first step? 3x minus 6 is 0. What would you do to solve it? You'd add 6 to both sides, right? It's no different. So let's start the same way. Our first step here is to add 6 to both sides because we want to isolate x to the 3/4. We want to get that all by itself. So our first step is to add 6 to both sides. And so let's do that. Okay, I'm just pretending I like life to be easy. And this is kind of messing with my mind, seeing that 3/4 there, but I'm not going to let it upset me. Okay? Now, what would be the second step in order to isolate x to the 3/4? What would I do now? Think of it as just 3x equals 6, Anna? That's right. Divide both sides. by 3. So far, again, you're using all of the strategies that you've learned long time ago for solving this. So x to the 3/4 equals 2. So you've divided both sides by 3. Now this is the only point that things look really different to you. You haven't ever solved, or maybe you haven't, an equation that looks like this. So this is what it says. Whatever x is, I have to take its 4th root and cube it and get 2. That's what it says. Now, right off the top of my mind, no number comes to me. What number can I take the 4th root of, cube, and get the number 2? It's got to be pretty small. Right. So, again, if you want to, you could call this if you want to, because that's a radical equation. These two things are exactly the same. It just depends on what you feel most comfortable doing. Some students really like changing everything to radical equations, because then they say, I know how I can get rid of this. I can get rid of this by raising both sides to the 4th power, because that will undo my radical, and then cube rooting both sides. Cube rooting both sides to get rid of the x cubed. Okay? Oh, you wouldn't write it like that. That's how I write it. You would write it like this. Cube root of 2 to the 4th. So that's your answer. X equals the cubed root of 2 to the 4th. So some students are more comfortable with radicals, but I just want to show you that it's really easy peasy to solve this equation from here and get exactly the same answer. It's just that instead of writing it with a radical symbol, you're going to just write it with exponent, a rational exponent. So remember, our goal is to get x to the 1st power. So what can you do to the left side so that you're left with x to the 1st power there? What could you do to that left side? Anna? You're all full of answers today. Multiply. So I know, so you want to write it on the board what you're thinking? Okay, because I think you got the right idea. I don't think I want to put a 4/3 out here, because then I'm kind of back a step, right? I don't want to multiply both sides by the number 4/3. That's not what I want to do. Oh, I used a big one. All right, so let me see what you're thinking, Anna. Yeah, yeah, yeah. Okay, gotcha. Okay, but you just said 4/3, didn't you? Well, put 4/3 there. That was right. Look at that. Hey. You could do it in steps if you wanted to. You could do 1/4 first and then cube it, but why not take care of both of those steps with one fraction? So remember, when we raise a power to a power, we multiply our exponent. So the number I multiply 3/4 by to get the number 1 is its reciprocal, 4/3, because 3/4 times 4/3 is 12/12. So whatever I do to one side, I've got to do to the other, and there's our answer. X equals 2 to the 4/3, and you can leave it just like that, 2 to the 4/3. If I ask you for the exact answer, this is what you give me. If I ask you to estimate the answer, say, round it to the 100th place, okay, then you would just throw it in your calculator. Some students asked me in the last class, how would you raise something to the 4/3 power? Well, I said, just like you write it. Let me turn this on first. I was going to try to make it bigger, but I'm not sure I can. Here we go. Yeah. All right. So there. Okay. So you go like this. You say 2. You use your little caret symbol here, raised. And then whenever you want to write a fraction for an exponent, you better put parentheses. And then you do just what this says, 4 divided by 3. 4 divided by 3. And there's your estimate. So if I wanted to round this to the 100th place, I would say, okay, I want to know if this is closer to 2.51 or 2.52. So I look at the number after it, 9, I round up. So then you say x is approximately, you never use equals, 2.52. So that gives you a rough idea of what the number would be. Okay, checking it really uses your powers of exponents to do. So let's go back to our original equation and let's check it. 3x to the 3/4 equals, what was it? 6? Is that right? Yeah. Okay. So what's x? X is 2 to the 4/3. So where I see x, I'm going to replace it with 2 to the 4/3. I raise x to the 3/4. Let's see if I can even check this. What's 2 to the 4/3 raised to the 3/4? 2. And 3 times 2 is 6, and you're a happy camper. It works. Okay. So that's how to solve equations with rational exponents. You now have 4 problems, group exercises. You can do them together. You can do them individually. And at 20 of them, I'm going to stop you, and then we're going to come back to using your graphing calculator to solve these problems. Okay, there are 2 methods to solving an equation like this. Let's review the method we did a few classes ago. Remember, a few classes ago, we said that if we had an equation like this, we call one side of the equation y1 and the other side of the equation y2. We graph them and we look for their intersection point. Remember doing that? Okay. This method is sort of a similar idea, but instead of making y1 this and y2 the right-hand side, you start to solve this just like you would if you were doing it algebraically. You bring everything to one side of the equation. So basically, you create a new equation, or excuse me, an equivalent equation like this. I should say -4. I don't know if that's clear or not, so let me go in here. So you basically subtract 4x from both sides and you subtract 4 from both sides. And again, depending on your prowess with factoring, you could factor this and solve it, but we're not going to go there right now. We just want to see, how can I use my graphing calculator to solve this equation? So you basically put this into y1, just the left-hand side. Okay. So you open up your calculator, you say y equals, turn it on first, y equals, and you, let me clear this out. All right, so let's go up here. So I'm going to put x cubed plus x squared minus 4x minus 4. Okay. So if I just graph that equation, I don't know if how much of some of you had a lot more high school math. You might have a sense of what this looks like if I were to graph it. Some of you may have no idea. So let me just graph it. I'm going to try Zoom 6, the standard window first. Okay. And let's see what we get. Oh, that looks pretty good. So that's what this looks like. This equation is asking, when does this, which is on your graph right now, when does that equal 0? So essentially you're saying, when does it, if I put this in for y2, y equals 0 is the x-axis. So you're actually saying, when does the graph of this cross your x-axis? That's what we call our x-intercepts. So you can see, because the answers to this equation are nice integers, you don't have to do any work. You can literally pick it off, -2, -1, and 2. So you can actually find the x-intercepts are -2, 0, the -1, 0, and 2, 0. Those are your x-intercepts. Notice, here's this part of your equation. All your y values are 0. And these are the 3 x values that give you y equals 0. So it's a little different idea. Instead of seeing where two graphs intersect each other, you're putting everything to one side and asking, really, where does it intersect the x-axis, which we call our x-intercept. So you're still using the idea of things intersecting, but you're making one of those things the x-axis. That's the difference. So to get the answer here, you do second calc right here, and you say, I want to come down to where it makes my equation equal to 0. So you come down to 2, and you hit enter. And now this is the only tricky part. You say, well, you could bring this over here so you're just to the left, anywhere to the left of the first thing, or you could actually put a value in here. So any number to the left of -2, you could say, okay, -3. There's my left bound, because you want your calculator to work within this little window and do all the calculations to find the number. Then you've got to find, so you hit enter. Then you've got to find a number right to the right of -2, but you don't want to go so far that you go by one of these x-intercepts. So you pick a number to the right of -2, but to the left of -1. So any number there. So I'm going to say -1.3. Hit enter. Then anytime you see guess, you always hit another enter. And voila, there's your first 0. It's called a 0 because it's the x value that makes this equation equal to 0. So that's one of your solutions, -2. Okay? That's a little different method than what we learned the other day. Does anybody know how to factor this? So if we didn't use our graphing calculator, do you know how to? Sometimes you can't factor them, and so you're graphing, you have some like wicked, ugly number that's not nice, like -2, -1, and 2. Does anybody know how to factor that? Nobody? I can't hear you, huh? That no one remembers. Okay. Yeah, you split it in half, right? So it's x to the 4th plus x cubed minus, well, what's the first, can someone help me? Was it -4x minus 4 equals 0? Yeah. So part of the problem is you got 4 things there, 4 terms, and you don't have a common factor all the way through. So chunk it up, pair it up like this. And then look at each individual. Now you have 2 things. You have a subtraction problem of 2 things. Then take each one of these parentheses individually and ask, what does this have as a common factor right here? It's x, I think a little more than x to the 3rd, right? So we get x to the 3rd times x plus 1. That's equal to x to the 4th plus x to the 3rd. Then what do you have common here? 4, so you got a minus sign out front. So you got x plus 1 as well. And now you have, wait a minute, this isn't working out. I guess I can't factor this because then I get x plus 1 times x cubed minus 4. Ooh. Oh, so I wrote the wrong equation. Oh, that always helps when I start with the right equation. What was the actual equation? X cubed plus x squared? Oh, that's much nicer. Okay. So we can use the same idea. That's why that didn't match what my calculator said. You pair them up. You pull out your x squared and you get x plus 1 left. You have -4 here. You have x plus 1 left. Oh, this looks much better. Where's your common factor now? X plus 1, x plus 1. Pull that out front. And what you have left is x squared minus 4. And then you factor x squared minus 4 into its conjugates, x plus 2, x minus 2. And those are the 3 spots where it hits the x-axis. It hits it at -1, we saw. It hits it at -2. And it hit it at +2. That was what we got. We call them our x-intercepts, and the x values of your x-intercepts are the solutions. See you on Wednesday. Everybody passed in their quiz, right? Everybody? Christopher, stay after class, please. Please bring the flags in your folders back. Thank you very much. Flags and folders.